So the idea is I want to cluster really large, data sets, right, very large data sets, and the way I am going to do it is the following, right. So I am going to do a very rough clustering at the beginning, right. I am going to do a rough clustering at the beginning where I am going to produce really tight clusters, right. I am going to produce really tight clusters, right, but many of them, and I produce a lot of small clusters. So essentially taking, suppose I have a million data points, I will reduce it to some 100,000 data points, but each one of them will be very small diameter clusters, right. I produce these things, and then what do? I take one representative point from each cluster and then I try to do my hierarchical clustering on that, right. So initially I do something that is little fast and dirty, right. So I might get the correct clusters, I might get a little bit off here and there, but then I do a second pass through the data and I will fix everything, right. So the way I do this is follows: I do one pass through the data, produce some rough clusters, right, and then I take the centroids of all these clusters, right, and then I do a proper clustering algorithm. I only work with these centroids, I do not worry about the million data points, I have reduced it to 10,000 centroids or 100,000 centroids, whatever, I only work with these 10,000 data points. So now I know small enough that I can fit it in memory, right. Memory is so large nowadays, you can fit a million data points in memory, but let us scale it appropriately, right. You have a billion data points, okay, and you are not able to fit all of that in memory, then reduce it to something small that you can fit in memory, right. So now what you do, after you have done the clustering, right, you will have a new set of centroids for all your clusters, right. Now what you do, run through the data once more and assign each data point to the closest centroid. So essentially you are making two passes through the data, once to produce clusters which are very tight, right, and then you take the representative points and then you do whatever you want, you can do an iterative clustering algorithm on top of that. So once you are finished with that, so what you do, you go back and reassign the data points to the nearest centroid. So the two passes through the data. So that is one of the things that you should think about when you are working with very large data sets. How do you minimize the number of passes through data, right. So if you can do it with one pass through the data, great, right. If you can't, okay, try to keep the number of passes minimal, right. If you think of k-means, right, very plain vanilla k-means, how many passes are you making through the data? As many iterations as there are, right. So every time you do an iteration, you actually need access to all the data points, because I need to compute the distance of each and every data point to the centroid, so I need to read the data all over again, right. So with a very large data, just going through that might be a pain if I can't store everything in memory, right. So if I want to read the data set all over again from the disk, then it becomes a pain. So we need to have something better than that, right. So what they came up with is a data structure called the CF tree. Came up with a data structure called the CF tree, where CF stands for clustering feature, right. CF stands for clustering feature or cluster feature, sorry, right. So what is a cluster feature? It is a 3 tuple, right. Suppose I have a cluster, right, that consists of some n points, right. Right. So I will denote the cluster by C, right. The cluster C consists of some n points, I will denote it as x1 to xn, right. In fact, I should do something more than this, I should say probably cluster J consists of cluster J consists of nj points, which I will denote as x1j to xnjj, right. So it consists of nj points. So this is the cluster. So the clustering feature corresponding to the cluster J will be the number of points in the cluster, okay, and the sum of the individual coordinates of the data points. Suppose my x 1j is consists of some V1 up till Vp, right. It will be too many indices, but right. So it is a point, my x1j is a point in a p dimensional space, right. So essentially each one of them is a point in p dimensional space, right. So this will be essentially, so my sigma, let us call the sum j and the, okay, I will come to that in a minute. So sum j is again a vector, right, sum j is a vector, and okay. So sum j, kth coordinate of sum j is essentially the sum of the kth coordinate of all the data points.
So sum j is just essentially sum of the data points.
Sum of the coordinates, individual coordinates. Sum j is a vector.
So if we consider data points as vectors, then it's just the sum of the vectors.
Sum of the vectors, yeah, that's fine. Data points as vectors is considered sum of the vectors. See, the reason I did not do that as sum of the vectors is sometimes people have been confused in the past. When I write sum of the vectors, they end up adding all the coordinates. Okay, so I didn't want the summation also to run over k. Right. So basically, if you think of a proper vector addition, it is just the sum of all the data points, right. But this notation is convenient for us when I want to write so I will take the square of the individual coordinates and add them up, right. So this is what I call the clustering feature, and the claim that they make in the BIRCH paper is that this clustering feature is sufficient for you to do some form of hierarchical clustering without actually knowing the identity of the data points, right. Suppose I give you the clustering features of two different clusters, right. Is there any way you can compute the distance between the two clusters? I give you the clustering feature of two different clusters, I give you CFJ and CFI, right. Can you compute the distance between cluster I and cluster J? I given you the sums, the squared sums as well as the number of data points. So if I divide the sum by the number of data points, I get the centroid, right. I can go ahead and compute the distance between the centroids, right. That gives me one way of measuring distance between clusters, right. I do not need to know the individual data points, all I need to know is the sum of the vectors, right. That is one thing. Is there anything else I can do? I am sorry?
There is some squared.
I have some squared also, we can use that. I can do the radius, right. So I am going to leave that to you as a homework, okay. Show me that you can compute the radius in terms of sum and SS, right. So I can actually compute the radius of the merged cluster also, right, based on the squared sums of the coordinates, right. So these are the things that I can do. I can even do the diameter, okay. So I leave you to work that out. So you can do this, you can do the centroid distance, you can do the radius, and you can do the diameter distances. You can't do single link, complete link, okay. So that is gone, right. But remember, what you are doing at this stage is trying to, the initial stage with the CF tree is trying to find small clusters, right, clusters of small diameter. So that is what you are interested in, right. I am not interested in doing single link or complete link at this point. what I am trying to do when I use the CF tree, when I build the CF tree, I will tell you how to build the CF tree in a minute. So, what I am interested at that stage is only in data reduction, right. I am only interested in doing data reduction, I am not really interested in actually finding the final clusters, right. So, it is fine. So, we can use either the centroid measure or the diameter or the radius and then keep some kind of a threshold, right. So, what do I do now is I start off from the root, okay. So, the root is going to have one cluster, right. So, you are going to have a clustering feature that is going to be there. So, as and when the data points come in, right, I start updating the clustering feature at the root, right. So, first data point comes in, my clustering feature will be 1 comma the data point comma the squares of the coordinates of the data point, that will be the first one, okay. Then the next data point comes in, then what do I do? 2 comma the sums of the two vectors, right, plus the sums of the squares of the coordinates, but I do this only if the 2 points are close together, right. If they are too far away, if the diameter is very far, right, very large, then I do not merge them together, I actually make it into a different cluster and I actually do the clustering feature there, right. So, I keep doing this, right, I keep going until I come to some point where I have too many clusters that I have thrown in at this point, right. So, essentially I start breaking the cluster into 2, breaking this node into 2. So, some clusters will go here, right, and some clusters will go here, right, and what do I do in this place? I insert a new clustering feature that summarizes all these data points. I enter a new clustering feature that summarizes all these data points, okay. So, why am I doing this? So, when a new data point comes in, right, I look at these 2 clusters and figure out which of those 2 clusters is closer to this data point, okay, and then route it down the tree there, right. So, if I keep all the clusters at one level, then every time a data point comes in I will be doing a very large linear scan to find out which cluster the data point should belong to. Does it make sense? Right. Suppose I start off with one cluster, then I produce 10 clusters. Now a new data point comes in, I have to check against all the 10 clusters to see which is the best cluster to put the data point in. Right. Now what I am trying to do is organize this in a more efficient manner, so that instead of taking order of 10, right, it is going to take some kind of a logarithmic factor here, right. I have to make 2 comparisons, so it will take order of 2, right, or depending on how many I put in here. Suppose I divide it into 2 and then put 5 here, 5 here, then it will take order of 6, right. But then if the tree becomes deeper, then you can see the savings, right, the savings will be tremendous. So, it will have some kind of a logarithmic compression. So, that is essentially what we do here. Yeah.
So, can you explain the starting point where you said you split the cluster?
Okay. So, initially what I do is I have one node, okay. So, I start keeping track of all my clusters here, right. Suppose I reach 10 clusters, let us say 10 is the maximum rate, I reach 10 clusters, a new data point comes in, I want to create a 11th cluster.
How do you determine that 10?
I am sorry?
How do you determine that 10?
Various factors, it depends on what is your memory size, right. So, and in fact you have to go even further down actually. So, it depends on your page size, not just on your memory size, right. You want your each leaf to span multiple pages, right, because a single access could actually lead to more page faults, right. So, you want to see if I access one entry in a leaf, I would really like the entire leaf to come into the memory and stay there, right. So, there are all these kinds of considerations. When you start talking about really large data, right, you have to start going into the system level of things, right. So, you have to know how things are stored, you have to know how things are accessed, right. So, here let us say I picked 10 for somehow, right, I said 10 is the number I am going to store, and what are these numbers? These are essentially 3 things like this, right, each one of these only 3 things like this. Right. At some point I say, okay, even if I have a 4 KB page, even like 100 clusters, I should run out of space, right, I will say no, I want to break it, right. So, then what I do is I split this and I put 10 here and I say another 10 here, I am sorry, put a 5 here, put another 5 here, right, and then I will start off with 2 entries here, right, instead of having 10 entries, okay, they will all go down, I will get 2 entries here, right, and each one of them will be, so the first entry will be summarizing the first child, the second entry will be summarizing the second child, right. Now when new data points come in, I can try to shove them into this, right, and then at some point it will come to a point where this thing gets filled up, then I will split it into 2, right. So I can do one of two things, I can actually push it further down, right, or I can split it into 2 and add another entry there. Which is better? Huh? Sorry? It's not bad, it's like 10, right? I mean I have 10, I have space to store 10 CF features there, right? So I could either make it broad branching, and or I could make it deep. Which is better? Broad is better. Deep is better. Broad is better. So if you choose to go broad, when do you go deep? When what gets filled up? When this gets filled up, and then you only push it down from there, is it? No, yes, right, that's the way to do it. Don't doubt yourself. What you said was correct. Okay, I just wanted to see how sure you are of your answer. So essentially you keep broadening it, right? When this gets filled up, then again you split, then everything goes down one level. Okay, so keep doing this and until you have gone through all your data points. Okay, so that the small point here is to notice, so I am not doing a numeric example, right? If people are interested in a numeric example of how BIRCH works, you can refer to the BIRCH paper. So we will put up the BIRCH paper online, right? We will, right? Yes, we will put up the BIRCH paper online. Okay, so what will happen is, suppose a data point comes at the very beginning, right? So it will get associated, let us say, with this cluster. So for that cluster I compute the clustering feature, I add it to the clustering feature in that cluster, right? But then later on, as I keep going down, more and more data points will come here and some more data points will come here and so on and so forth. It is likely that if I try to insert the data point again into this cluster tree, right, it may go into some other cluster because things move. So there is this significant order effect, right. So sometimes what people do with the BIRCH is, after they have grown the tree to some point, they stop, okay, and then they try to do some kind of rebalancing. Okay, that is just an additional optimization step. You need not do the rebalancing step, you could just grow the CF tree in one shot, right. More often than not it will work. Okay. So at the end of the clustering, what you will have is, you will have a lot of leaves at the bottom, and each one of them containing say 10 clustering features, right, and these are your final clusters that you want. That was the question. Are these your final clusters? No, right. See, remember I told you the first phase, when I am constructing the clustering features, the CF tree, all I am interested in finding are tight clusters that I can then use as representatives for doing a further clustering, right. So what do I do now is go into each of these clustering feature, compute the centroid, I can do that, right, divide sum by nj. So corresponding to each entry in each one of the leaves, okay, I will get one data point, which is the centroid, right, and then I go start with these centroids and do a clustering all over again. Here I can do whatever I want, I can do single link, I can do a complete link, whatever. So because I have reduced the number of data points to something small and manageable, right, I can do whatever clustering method I want on these data points, right, and then what I do is, the final centroids I get after I do that clustering, I go back and look at the data all over again, right. So I scan the data once when I build the CF tree, right. Now I scan the data again after I finish my clustering, okay, and then assign the data to the nearest centroids.
Why do you need to do that? You just need a new point and you can just assign it according to the.
No, I need to cluster the whole data, right. I need to know what cluster you belong to, right. So I need to know that, right. So like I said, I cannot trust the identity here. So, in the initially I said okay, this clustering feature got the data point I, okay, now so the same clustering feature would have percolated down to the leaf, right. I can't say that okay, this clustering feature whatever cluster it goes to, that is the cluster that the data point belongs to, because that would have drifted away, this centroid could have drifted away due to the later data points. So, I cannot do that, right. So, it is not the mapping between the CF the clustering feature and the data point, okay, is not static, right. It would have changed, it would have drifted away, therefore, I have to do the second round of assignment. Okay. People understand BIRCH? See, I really like BIRCH, because it's a very simple algorithm, and it also allows you to handle very large volumes of data. I usually ask people to implement BIRCH in one of the programming assignments, okay.